We'll continue from yesterday. We are going to continue with the graph problem. Okay.
Over an approach we can use for the shortest path problem. So here we have another graph problem, and your graph is going to be given as an edgeless. So the first thing you should probably do is, of course, visualize this graph, and in the context of your code, it probably would be best if you converted it into an adjacency list. Since we've seen that pattern a few times in some recent problems, I'll leave that part to you. But we're going to end up with a graph that looks like this, and in this problem, we're also going to be given two nodes. Here, let's say W and Z. What I want to do is return the smallest path between these two nodes. And here I have two obvious paths, right? One way I can get from W to Z would be to go through X and Y. And there I can see that that path length would be 3. Do note here that we're going to consider the path length as the number of edges within the path. So not the number of nodes, right? So that means, how do I calculate 3 here? Well, it's really just 3 lines, right? 3 edges. That's one way to get from W to Z. Another obvious way to get from W to Z would be to go through V, in which case I would only need to use 2 edges. So that path length is of course 2. And in this problem, what I want to do is return the smallest possible path length. So I should return the final answer of 2 here. So we know that this problem is going to require us to do a graph pathfinding algorithm. And the question is, which one should we take? We either can choose, of course, a depth-first traversal or a breadth-first traversal. I'll cut to the chase here, and both of them would actually give you a strategy that works, meaning you can solve this with either a depth-first or a breadth-first strategy, but maybe one of these algorithms would be better than the other. So let's consider the possibilities. So let's say I had some large graph, we'll think abstractly right now, so kind of just looking at an abstract example, and let's say I was stepping through some depth-first traversal. Let me say I have my starting node in yellow, and I'll have my target node in blue. So what I want to do is, again, figure out what's the minimum path distance between these two nodes. Obviously, you know, just in the long run, you should get an answer like 2 here, right? Because 2 is definitely the shortest path between these two nodes. If we did a depth-first traversal, I know that depth-first would force me to look in one direction as far as possible until I have to switch directions, right? So from my starting node in yellow, let's say we move to the right. That'd be 1 edge, and move to the right again, 2 edges, move to the right again, 3 edges. And at this point, I can't move right anymore, so let's say we move downward. So I have 4, 5, 6, have to switch directions again, 7, 8. And at this point, we kind of already see that this is going to end up possibly getting to the blue target node, but it wouldn't be the shortest path. Something unfortunate here is, although my start and end nodes are really close together, a depth-first traversal could be unlucky in that it may search in a totally wrong direction and snake all the way through the graph until it eventually finds my target node, at which point I definitely don't have the shortest path. So I think a breadth-first traversal is going to be more useful here. So let's say I started at my green node, still my same starting point, and if I did a breadth-first traversal, I know that breadth first means I'm going to explore all of the directions very evenly. So it would look like this. So I would explore all nodes 1 edge away from my starting point. And then from there, I would begin to explore all nodes 2 edges away from my starting point. And at some point, I'm going to hit my target node. And if it's the first time I'm seeing my target node, then by definition, I must have just found the shortest path, right? The shortest path would just be 2. So that's my high-level argument for why a breadth-first search is going to be more useful, in my opinion, for this problem. Let's step through this process a little more algorithmically. So let's say I had my original graph, and if I'm going to do a breadth-first traversal, I know that I have to use a queue, right? No matter what, a queue is what gives you that breadth-first order. And what I'll do is, as the items of my queue, I'm going to store not only the nodes, but also the distance from my starting point. So that means I'm going to initialize my starting node on the queue along with the distance of 0. And that represents the fact that, all right, that node of W is 0 edges away from the starting point because it itself is the starting point. So at any point in time, the items of my queue are always going to be pairs, right, of node, comma, distance. So now we can begin our general algorithm. I'm going to keep iterating while my queue is not empty. A single iteration of breadth first would remove the front item of my queue, and I'll label it as my current node. At this point, I should check, all right, is my current node of W the thing I'm looking for? It's not, so I need to explore W's neighbors. So I can look at the X node, and I know I need to add it into my queue. But when I add it into my queue, I want to make sure I tag it with a distance. So if my current node has distance 0, I know that a neighbor of this node would have distance 1. So I just increment the current distance by 1. So onto my queue, I put an item that says x, comma 1. And I have a similar scenario for this v node. It's also a neighbor of w, and so I put v, comma 1 on my queue as well. At this point, I can go to my next iteration, remove the front of my queue, so I look at the x, and then I look at x's neighbors. Do bear in mind that because I have an undirected graph here, x really has two neighbors, right? It has w as a neighbor as well as y. So something you should already know is I need to track visited. In other words, when x is going to consider its neighbors, it should really only care about the y, right? I don't want x to put w back on the queue because then I would get an infinite cycle. So I'm just going to look at the y over here. I'm going to add it to my queue. Because I know my current node of x has a distance of 1, y must have a distance of 2, always just incrementing the distance by 1. Cool. And then I'll carry on with this algorithm. I remove the front of my queue now, which would be the v node. And at this point, I can consider v's neighbors. And I do see that one of its neighbors is actually the z node. That's the only unvisited neighbor. I'm going to be sure to add z into my queue and tag it with a distance of 2. Right? Because if my v has distance 1, its neighbor would have a distance of 1 greater. And at this point, you can already see how this algorithm is going to work out. Eventually, this z node is going to leave the queue, and that would actually be my target node. So since I've added a node into the queue that matches my target, I know I have my final answer. The 2 here does represent the number of edges we took in that logical path. And I would, of course, just return that 2. So for the most part, this algorithm just sounds like a classic breadth-first traversal using a queue on a graph. The only interesting bit is now we're also going to track the current distance. You know, when it comes to counting the length of a path, you need some counting mechanism. And so if you begin your queue with your starting node with a distance of 0, every time something leaves the queue and adds its neighbors, it should increment that distance by 1. And like you already guessed, this algorithm is pretty efficient because we don't have to traverse through the graph more than once. So we'll say that this has a linear complexity. All right, I think I have everything I need to code up this one. I'm sure you're wondering about these implementation details. So what you want to do is possibly give this implementation a shot on your own. And if you need some help, you can find me in those walkthrough videos. See you there.
Let's go through the problem of it. Shortest part. Okay. So we have given an age. Okay. So we need to convert it to an agency. Adjacent. Okay. Which is we need to change it into the graph. Okay. So change this into the graph. All we need to do is start from the age. So we're going to create an. We should first include order. Okay. And we also need a list of visited elements. So we'll add another unordered set. Okay. Let's start again. So first let's start with change the graph. To change the age into graph, all you need to do is create map of first string vectors of string. Okay. Let's name it graph. Let's look through all the edges. Okay. So while it's a tuple, so we have a pair. So all you need to do pair all you need to do is look through all the edges. Get the first and second, so that will be First, we get this. Let's go to the previous problem to see how we were getting this pair. Okay, so how to get this pair? Pair the first, pair dot first, and pair dot second. Okay? Now in the graph, undirected is, see, go to the previous problem. In on the graph, it's easy, like you can go to undirected path. Okay? Std this. Okay, so this problem again. Pair. Okay, and now we need to do is push those into the graph. Okay, graph gra push. What do you push? First push, second second push. So now what we need is we have a graph. So as a graph, let's create a queue. Okay, add queue of pair. Okay, or tuple. Pair or tuple. You can do anything. Okay, first time into pair of pair pair of, let's say, pair of string and int. So that will be distance. Okay, queue. Now what we need? We need more. So we need to add the first element of the graph to the queue. Okay, so it is undirected graph of two nodes. This and the function should returns the length of the shortest path between A and B. Consider the length as the number of edges in the path, not the number of nodes. So if there is no path, return A, and then also return -1. So what we can do is simply we have this. So if it is unordered, because undirected graph, so is there a graph disconnected? Like, is there possibility of a graph being disconnected, having two graph in graph? Okay, so let's say first let's consider that not being the case. Okay, so what we're gonna do is basically simply what we're gonna do, we're gonna just add the first element here, push what should it push? So push. Okay, We have a graph, so we have a value. Choose the first element of the graph. Should we create another going through the graph? We have created efficiency. Now we need to again go through the pair. First and second, I will need to create what do you need? We need to create another one so that we can. Let's say let's create another set. Okay. Set of what you call nodes, all the nodes. Okay, all the possible nodes. Get set of what string that will be all nodes. So basically, what we're gonna do is we're gonna all nodes dot short first. Yeah, all nodes dot short second. Okay, so now we have all of these string. Start at the first. We loop through all the nodes in this node, or we can do graph all the first in the graph. We do not need, if we want, we can skip this. Okay, let's skip this one. Something like this. What I'm gonna do is we're gonna each pair and pair graph first. Yeah, sorry. Instead of commenting, let's create another one. It's named visitor. Visitor. So what are you gonna do? Check if pair find pair dot first. First again. So if we haven't visited that node, what you want to do is, if we haven't visited that node, we're gonna go through that node and all the nodes corresponding to that node. Okay, so yeah, the first, so we will start from the. So if we do this, we will. If we do this, we'll find a way. 100 find. So there is not possibility of disconnected graph. So if we do this, then that means there is a possibility of disconnected graph. First element from the graph. You do not need to do this again. It's out. Let's just view that. sorry, we must have the starting node. So starting node and node. So we need to push or what do you push? We push starting node, that is node A. Okay, and value as 0. Okay. So we do not need to do this. Okay. Now while our queue is not empty, queue is not empty, what we're gonna do is simply we're gonna get the top element from the queue, that will be, let's say, current, that will be current element from the queue, that is the top element. Let's do top from the queue dot top. Okay. And once we have top element from the queue, what we're gonna do, we're gonna pop the queue, and then before popping, what we're gonna do, we're gonna check if top dot first equal our node B, that is our destination. If that's the case, we're gonna return what we're gonna return. We're gonna return simply what we're gonna return. We're gonna return top dot second. Okay. Otherwise, we're gonna go through all the neighbors. And okay, before popping, we need to do one more thing. We're gonna add that to visited. Okay, so visited dot push. Dot okay, top dot first. Let's insert that. Okay. What we're gonna do is we're gonna look through all the neighbors of the top. Okay, or current. So for each neighbors, that will be string. Okay, but let's do auto st so let's be your neighbor of that will top will be graph top dot first. Okay, our neighbor or the neighbor of this. So this will be string. So let's do string. Okay, now before adding the neighbors, we're gonna check again if find neighbor. If we do not find the neighbor, we're gonna add it to the queue. Okay, queue dot push. What we're gonna push? We're gonna push neighbor, whatever the top dot second plus 1. Okay, if we haven't visited, we just top the second plus 1. Okay, and one thing more, if let's say our neighbor, if we haven't visited our neighbor equal, let's say node E, we can whatever simply gonna return whatever top dot second plus 1. Okay, now let's continue. Otherwise, let's return -1. Okay. I think we do not need to do this over here. But let's say our the first element is well, let's say node A equal to node B. So we need to return 0, 0 because our destination and start node is both the same. So we need to do this here. If the neighbor, so we all need to do this. If we do not do this, we need to do get this case over here. So we need to do okay. This. Yes. Vector. People. This certain names were expected double column. Error found this name specified expected double column expected. Pair has not been declared. We're declaring it out of here. Copy that, paste it over here. Let's remove that. Let's do this. Yeah, this should work. Again to undirected graph. We are given an age. All we do again is with a tuple pair is study vector. This should work. Tuple ages. Why is this not working? String, string. So that is string, string. So we're getting this string. We're creating a graph. String, 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 string. Sorry, one, while, for, after, push, after first push, second. Sorry, this is the vector, so we need to do push back. And y, t, here. So, what do you mean? Pop. Okay. So, 2025. This should give us this. Sit. Emitter. T. Okay. State. Right, front. We have front because it's a queue, not a step. That's it. And just visit the find, something like first find. So we got the answer. Okay. Well, this is it. Okay. This is the solution. Let's go to the walkthrough video.
Hey programmers, Alvin here. Right now let's go over the C++ solution for the shortest path.
But let's say there could be a situation if the graph does not connect with the other graph. But okay, so that will return -1 because if it is not connected and if there is two graph, first graph has a start node and second graph has a end node. So basically if we start from the first graph and we'll go through all the neighbors of that graph and we'll end up with visiting all the nodes of that specific graph, and we do not find the node B, that means we cannot even reach node B from the node A, so we just return -1. Okay, so this solves that problem. Okay, because we are returning -1 if we cannot even reach there, not like from any node. Okay, so from the start node. Yes.
Problem. So we'll jump right in. As always, make sure you watch the approach video first. This is going to be a kind of new pattern for us. And so to get the ball rolling here, what I want to do first is to convert this edge list into a nice adjacency list, because it's easier to do our classic traversal algorithms. In the long run, I want to implement a nice breadth-first traversal. So to start that conversion over here, I'm going to break that into a helper function, and eventually it's going to return a type of unordered map. That's how I like to present my adjacency lists inside of C++. So I'll bring in that nice header, unordered map. And so eventually my function is going to return an unordered map. The keys of this map are going to be just strings, right? Because it looks like the IDs of my nodes here are strings. The corresponding value of the map is going to be a vector of nodes, so a vector of strings. So pretty nested type over here. I'll just copy this. So this will be the signature for my return type. I'm going to create this function. I'll call it make graph. It's going to take in just the edges, which is of this longish type over here. Nice. And so for this helper function, you've seen this pattern before. I just want to eventually return this data. So I'm going to create an empty map, eventually return it. And in between, what I want to do is iterate through every edge. So I can say for, I'll say auto edge within edges. And for that edge, I'm going to unpack its two members. That is the A and B node, I'll call them. And I want to make this a symmetric graph, meaning it should be undirected. So A points to B, but also B points to A. So I can say for the neighbors of A, push B into it. But likewise, for the neighbors of B, push A into it. So that's good to go. I do know in C++, because I have the type declared over here, even if it's the first time I'm adding a element into that vector, it would also already exist as an empty vector, which is good to go. So I can just go ahead and push back always. So that's going to be my nice helper function over here. Let's make sure we don't get any wild errors right now. So maybe I'll just call my helper. I'll say make graph. I'll give in the edge list. And that should give me back my nice graph. Save that to a variable over here, right? Awesome. And for now, just so I get some running going on, I'll just return 0 arbitrarily. I want to make sure I don't have any compile time errors for now, because we're going to need quite a bit of code for this one. All right, so I'm feeling pretty good about that. No crazy errors. But now to solve this one, what I want to do is start to implement my breadth-first traversal. Because I want a shortest path here, I know if I do a breadth-first traversal starting at node A, looking for node B, the first time I encounter node B, that must represent the shortest path, right? Because a breadth-first traversal kind of explores outward in all directions. Path distances only get longer as I continue a breadth-first traversal. So because we want a breadth first, I'm going to need some additional header here. I'm going to need my trusty queue, right? So I'll start by creating my empty queue. So I'll say std queue. And the type I want to store in this queue is going to be really important. I'm going to need not only to store the nodes, which is just a string, but I also want to store the distance it took to get to that node, just like we said in the approach video. So I'm going to have to store a tuple. I already have the header, so that's good to go. I'm going to store tuples, and every tuple is going to have two things. It's going to have a string representing the node. That's nothing fancy. It's also going to have an integer representing the distance to that node. So that'll be my initial queue. I want to initialize node A onto the queue. So I can say queue.push. And when it comes to the shape of this data, of course, it's going to be a tuple, exactly what I just said. First thing in the tuple is going to be the node itself. So I'll say node A. And the starting distance will be 0 for node A. Right? Over time, I'm going to increment that number, though. Awesome. So now some classic code. I'm going to iterate while the size of my queue, so while queue.size, while it's bigger than 0. So I keep going here. And for the most part, some classic logic. So a single iteration of your breadth first reversal means you look at the front of your queue. And you also want to eventually remove that front element of your queue. And when I actually grab the front element of my queue, I know it's going to be a tuple like this, right? So I think I'm going to unpack immediately from it. I'll just use auto, make it a little quicker here. So I know the first thing in the pair is going to be my current node. I'll just say current. The second thing in my pair is going to be the distance. I'll call it distance. Nice. So there I have the current node and its distance. What I want to do is now consider this current node, and maybe it's the node I'm looking for. So maybe it's node B. So if the current node I just removed from my queue, if it's the same as node B, then I just found B, meaning I just found the path. How can I return the distance to that node B? Well, just return whatever distance just came with that node, right? I'm tagging every node with its proper distance from the starting point. Just return distance over here. Now when it comes to adding the children to the queue, like we're used to, just iterate through all of the children or neighbors of this node, be a more correct term. So I'll say for, I'll just use auto again. So I'll say for auto neighbor within graph of this current node, add this neighbor. So I'll say queue.push. Be sure to use compatible types though. So always be sure to push a tuple onto your queue, right? So when I push the neighbor, I want to make sure the neighbor is the first item of that tuple. And the corresponding second item would be the distance, which would be distance plus 1, right? So if a parent node has like a distance of n, I know its child would have a distance of n plus 1, right? Because it's exactly one edge away from its child. That way I get the nice counting logic. Awesome. So something I also want to work in this problem is to be sure to avoid any infinite traversals. Like we're used to, for most of your graph problems, you will need to track visited. So let me bring that in. You've seen this pattern a few times. So I'll bring in my unordered set because it gives me O of 1 lookup. And what I'll check over here is, or what I want to create rather, is a nice empty visited set. So visited is eventually going to store a bunch of strings. And I do want to initialize node A onto visited, right? So move this down here, and I'll say visited.insert node A. So something important for me whenever I design my breadth first like visited logic, whenever something enters the queue, you should mark it as visited. You don't want to mark something as visited when it leaves the queue. That way you actually might still double visit them. So always add it when it enters. So if node A begins on the queue, then node A must also begin in visited, right? And with that out of the way, now I want to work in that logic over here. So before I just add the neighbor into the queue, only do that if they're not visited yet. So if the visited.count of neighbor, so only if that's 0, meaning I haven't visited this neighbor yet, then I can do this logic, right? And once I add them to the queue, like I just said, be sure to add them into visited. So visited.insert this current node, so just the neighbor. Final thing I need in this problem is when they tell us that a graph does not have a path between A and B, you want to return -1, it looks like, just like this. So when would that be the case? Well, if I finish this while loop and my queue is
Let's say, okay, for some case, let's say we have not
empty, that means I would have
visited.
never hit.
We haven't visited this one. But if we do this, if we insert the visited over here, all the neighbors which we haven't visited, we have just gone through the. We have once we add to the queue, when we pop, we have visited that node. So this should be visited, should be over here. But this is also fine. But if we are doing this, the node A, the top node never will never be on the visited, because top we have never added the whatever the top front node, that is A, we never added A to the, sorry, we have already manually added it over here, okay, to visited. So we have added this visited. So all the neighbors we have added it to visited. Then we have +1. So if you have visited, so we have visited queue.pop push. Let's check. So we added when we add to the queue, we are marking at visited instead of when we pop the element from the queue. In my solution, whenever we pop the element from the queue, the front element from the queue, we check, we mark it as a visited. In this, whenever we look at its neighbor, we are marking it as visited, and then in next situation from the visited node, that is queue, we checking this one. So let's say we have already visited that node, but in that we have to complete even more iteration to get that node. Let's say there's a 5 node from one node, so we have visited, let's say one of the node is destination node. So if the one of the node is destination node, we went through that, for this loop we went through that, mark the destination as visited, but still we have added 4 more neighbor node to the queue. So we'll go through all the 4 neighbor node before going to the current node, the destination node. Okay, to checklist there is 5, we add 1, 2, 3, and 4 as 4 is our destination, so we add 4 in the queue. So first we'll pop 1 from the queue, then 2 from the queue, then 3 from the queue, then 4 from the queue, and we'll check one neighbor, two neighbors, and three neighbors. Then we'll go to the four, which we are marked as visited, but we have we currently, when popping that or removing that from the queue, we are checking if that is our destination or not. Okay.
This if statement
So,
returning the distance. So just do a late returning.
so basically, this we are traveling even more. We are iterating even more than we need to get to the solution. Okay.
That might do the trick.
Thanks.
Awesome. So you have a lot of code in this one. Let's go ahead and give this a test run now. So looks like here I'm having a little compile time error. So let's double check this. Looks like getting a few errors. Let's start on line 24 over here. So I have std visited. Oops, that's not right. I meant std unordered set, whose name is visited. That's better. Let's try that. Awesome. And there's our breadth first solution for the shortest path problem.
Mm. Let's go to the next problem. Okay? That is island count. Okay.
This island count problem. So in this problem, we're going to be given a 2D array representing a grid of land and water. So here we have L characters representing land and W characters representing water. Let's try to visualize this. In this problem, what we want to do is return a number representing the number of islands on the grid. We're going to consider an island as a vertical or horizontal connected region of land. So in this particular example, we should return 4 because there are 4 different islands. We can label them.
Basically, this problem is simply a component count problem. Okay, so we'll count how many components we have in the problem. Okay.
As such. This is going to be a new type of problem for us, and we should really think about it as if we have a graph. I'm going to refer to these style problems as a grid graph. And so although we're not given any explicit like nodes and edges, I can still think about positions of this graph as nodes. So for example, let's consider the indices here. So I have my row indices along the left-hand side and my column indices along the top. And I can designate any position of this grid using a pair of row and column. So for example, if I looked at position 3, 4, that would be this position over here. And what I should do is mentally think about a position as if it's a node. And if I'm at some node, I do have some potential neighbors. Given any position of this grid, I have at most 4 neighbors in the up, down, left, and right directions. Given any position of the grid, it's really easy to determine what our potential neighbors are. It's really just a matter of adding or subtracting 1 from either the row or the column. Let's generalize this formula. So let's say I was at some position, we'll call it RC. If I wanted to go upward, that would mean you decrement the row by 1, keep the column the same. If you went down, that would mean increasing the row by 1. If you went to the right, that would be increasing the column by 1. And if you want to go left, then you should just decrease the column by 1. Do bear in mind that the top left position of our grid is going to be 0, 0, and that's why we have this type of arithmetic rule. So now that we're starting to frame this grid problem as if it's a graph, we can use some common patterns. I know that this problem is really asking me to count the number of connected components or the number of islands on this grid. So I'm going to need some iterative code, probably some nested loops, to just iterate through every potential island and start some traversal at that island. So when it comes to our iterative code, we just want nested loops to iterate through every row column. That means the iterations should look something like this, just moving left to right until we finish a row, in which case we can go to the next row. But let's actually iron out the main logic that we need in our algorithm. So let's say we start our nested loops from the very beginning. What I do is check my current position. What I want to do is check if my current position is land. Right now it's water, so I can just continue. On the next iteration, I do have some land position, and since I'm on a piece of land right now, what I want to do is explore this land region as far as possible, probably using some depth first traversal. And do bear in mind, like most of our undirected graph problems, we're going to need to be sure to mark things as visited so we don't get trapped in any infinite cycles. So for example, if I start a traversal at this position, I can go downward, but I can also go upward from here. And I can bounce back between the two, going up and down, giving me an infinite cycle. So we know how to fix this using all of our graph mechanics, right? Just use a visited set. So if I do a depth first traversal starting at this position, I know I'm going to mark off all of these land pieces as visited. And what I also want to do is make sure that I increment a count representing the fact that I've just explored some new island fully. So right now my count's 0. Since I just finished exploring something, now my count is 1. And at this point, I can fall back to my iterative code to scan for another island. So I move to the right, it's water, so continue, water, continue. Now I have another island, and again, I just do some depth first traversal through it. And of course, I increment my count. This pattern will follow, right? Eventually, when I hit the new row, I could be at a land position, but I should also make sure that this land position is unexplored, right? So since I'm at position 1, 0, and this land has already been explored, I don't need to begin a depth first traversal. And I also don't need to begin a traversal here. And this continues, avoiding starting a traversal wherever I have a visited piece of land. We know eventually we're going to hit a new island, like this one, where I have a piece of land that is unvisited. So at that point, that's my criteria for starting a new depth first traversal. I explore this region, increment my count, and continue business as usual until I hit this final island that is unvisited. So I visit it and increment my count. And by the end of my iterations, I should have my final count of 4. So that logic is actually pretty straightforward, just a variation of our classic connected component counting logic, except now we're adjusting the criteria we use for looking at neighbors, right? Our neighbors are actually going to just be either above, downward, to the left, or to the right of our current position. When we talk about the complexity of this algorithm, we should consider the size of the input and the fact that it has 2 dimensions, right? So if I say that R is a number of rows and C is a number of columns, well then the iterative code is pretty straightforward. I know that's going to give me R times C iterations. And if I also consider any potential depth first traversal I do starting at some land, in the worst case, I could have one giant island, which is also going to be R times C. So the overall complexity is just going to be R times C. The space complexity, for a very similar reason, is R times C, because imagine that we mark all of these positions as visited. That probably means we'd have to add them to some set. Right? So I have R times C different positions, and by the end I could add each and every one of them into my set. This space complexity of R times C also includes any traversal related data structures like stacks or queues, depending on how you implement this one. So overall, this is going to be a very efficient solution to solve this one. What you should do is probably give it a shot on your own first, and if you get stuck, you can find me in the walkthrough videos. I'll see you there.
Problem, okay. So we have given this like this. Yeah. We have grid. Starting at vectors of vectors. So what is 0, 0? This 0, 0 will have water. What we can do is okay, on the water, okay, we need to book all the big. What we want to do is for each we need 2 loops. Okay, one loop to go row-wise, another loop to go column-wise. So what we're going to do is simply each row starting at 0 while row is smaller than then is grid. So okay, splish. Again, what we love in column that will also start at 0 while column is smaller than grid 0 dot size. Okay, now we have to go through all the loops. Okay, so now check our grid row column will equal water. It's equal to water. What I will do is simply continue. Okay. We need another variable here. Okay, mountain island that we start at 0. Okay, and I return. Okay, so if it's water, we'll just look through it. If it's not water, what we're gonna do? We're gonna do. We're gonna check its neighbor. If not water, we need a stack. Okay, so what we do is we're gonna create a stack of pair. Okay, that we have int that will position uh, the position. Okay, first position, second position. And let's name it stack. Okay, so we have one issue. Okay, if we are any at any corner, we need to be sure to not get outside that corner. Okay, so what we're gonna do is we'll create int that will be go size dot create dot size grid gets size and size with column size. Now what I'm gonna do is we need a formula. So we need a formula to get its top, right, left, and bottom. Okay, and before doing that, we need to we have to go and call basically we need top, left, right, and call. Once we have found an water, what we're gonna do is once we find a land, we're gonna call another. Let's say we create another function to call that. So let's say we found it here. So we need to take its left, right, up, and down. That would be let's do for top. Okay, first. So whatever the row position, our row will be same. Row will be whatever our row is. All it will be sorry. Our row will be row minus one. Okay. This will only happen if our row is not equal to 0. If sorry, if row is our row equal 0. So if we are in the top row, let's say if we are on the top row, all we need to do is it's up. There is no up. Okay, there is no up. Uh, let's do it 0. We do not need to count how many we need. So all we are going to do is if we are on the top row, its up will be similar to this one. Okay, we can do is check only if row is not equal to 0, then we what we're gonna do is we need to go up or down. What we're gonna do is go down if only row is not equal to, that will be whatever our 1, 2, 3, 4, 5, 6. So whatever our row is, so whatever our row dot size -1. This is not equal to our row dot size -1. Then only we will gonna do this. Otherwise, we are gonna do nothing. Okay. So now let's do this for uh, right side. Okay? Let's do right side. We're gonna check if our column is not equal to 0. This, if this is not equal to 0, then only we're gonna do this. Sorry, this will be for left. To right, check on it. Right, if our column is not equal to our wall size -1, okay, then only we're gonna check its right side. So let's say if our row row is not equal to 0, what we'll check, we're gonna check its top element. So that will be row, check its top element. That will be go through by going through its neighbor. Okay, so whatever our current node is, so our current node is grid uh, row column. Okay, so we're gonna do is we're gonna check its up. Check its up. So whatever grid, if it's not equal to row -1 and column, row -1 and column equal land, equal, let's say land. What we are going to do is we're gonna add this to the queue. Okay, start. Let's when this is not water, we need to add this to the queue. Okay, so that will be row and column. Today is okay. Push what we want to push, we're gonna push row and column. That is this row and column. Whatever our stack got. Okay, so we're gonna push this. Then we're gonna do keep on checking while our stack empty. Keep on checking its neighbor. It will check its neighbor. We will do this. Yes. Let's say another. We'll have pair this pair. Okay, that will be current. Okay, that will be stack dot top, whatever the top of the stack is. Then what I'm gonna do is we're gonna pop that from the stack. Pop that from the stack. Mark it as a fidgeted. So instead of marking it as fidgeted, what we're gonna do is we're gonna change it from L to W. Okay, whatever that position is, we're gonna change from. Simply let's do this one. So whatever the current what position is, whatever it is, we're gonna change it to the that will be because playing like this will auto. Okay, it's work. It's a tuple, it should work, but it's a pair, so it should not work. Let's leave it. Read comment first will be is it to the water. Okay, we'll change our current element go to the water. We'll pop that from the dish. No, we'll check its neighbor. Okay, we'll add its neighbor to the stack. Okay, so if our row up, if our current that first current is not equal to 0, so that is our row. If our row is not equal to 0, whatever our current that first minus 1 current that second. Okay, we're gonna add if current that our top element is let's say land, we're gonna add it to the stack. Okay, push volume push one and just second. Okay, same thing with the row down. Okay, if our if we are on the lowest row first is if this is not equal to last row. If you are not in the last row, we're gonna check the down. If you are in the last row, we do not need to check the down. If you are the first row, we do not need to check the up. Okay, so let's check the down. Okay. So what we're gonna do is simply do again. Okay, paste instead of minus do plus. So we're gonna check down this. Then what we're gonna do, we're gonna put plus one to the stack. So what we're gonna do, we're pushing next position to the stack. Okay, same with this. So for the left, what we're gonna do is whatever our current just second. Okay, if it is not equal to 0, what we're gonna do is copy this. Take whatever the current the first is minus 1. If it is not, if it is land, what I'm gonna do is simply push the next position, that is left position to the stack. Okay, and again let's do this first and that Second, if we are not in the last column, what we will do is check into plus a plus while it is not empty. Right? So that is we're checking all of its neighbor. Left, so this up, down, left, and right. So if they are land, we're adding it to the queue stack. Otherwise, we are not adding to the stack. Well, it's not empty. Once we got it empty, it's, once we loop out, we will loop count plus plus one. Every time, every time we find a land, we will do count plus plus. Go through all the connected land and we'll change it to the water that is marked as visited. Simply okay. So all we do is go mark that as visited. Basically, this is a mark as visited. So we do not add that again to the queue. Okay. Simply go and column. Run this. Line 6. Here. Basically, we completed this island problem. Okay. So what we're gonna do is we're gonna copy this exact solution. Okay. So to this number of island problem. So this is similar to this one. We have grid similar. Everything is similar. We need to do everything as same. Instead of L, we need to do it as if it is water. We do nothing. It is land. That is one stack. Okay. No, we run this one. Let's submit this. So we got the number of island problem done. Okay. Yes. And the last problem. That is minimum island. That is the smallest size island. So all we need to do is, let's say if we want the minimum island, it's a similar, totally similar problem. All we need to do is do everything similar, but instead of we need to count, but instead of counting this, we need to count. We need to return the smallest island. That's the problem. Okay, so smallest island. We'll have an, let's say, int result. Okay, that will be, let's say, max int max into int max. Okay, if okay, int, so okay. We limit our um, objective, which limits will attach. So okay, that is int max. That correct or not? Okay. So int max. Okay. So that's correct. Okay. So we have max. So all we do is once we find our land, we add it to stack. We create another variable. Let's say count. Okay. That will be 0. So once we find the land, every time we pop it, every time we go through the next land mass, we will increase the count. Okay, every time we pop it from the land. After iteration, after going through all the land connected to the the land we found, the starting land, what we are going to do is simply at the end the end of this loop, we're gonna check if our count is smaller than our result. So if it is, so in a result will be our count, return result. Okay, what's the problem? So include stack. Okay? Go test case true. Expected 9 getting 30. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6, 7, 8, 9. Okay, 9. Getting thing. So print we found a land and we go through all of the land. So we found this land. We add its row and column, that will be 0 and 0. We get the top element from this. Get it, which increase the count. So we go through, we add this and this to the stack, and we go through this, then add this and this to the stack, then we go through this one, we add this and this to the stack. So we keep on doing this. So guys, we so we start at 0, we count it. If there is a 9, we'll eliminate this and this to stack. Then we go over here, we add this to the stack. When we go over there, we add this to the stack. When we go over there, we add this to the stack. When we go over there, we add this and this to the stack. So we have already we added this and this to the stack, but we have already added this to the stack. So we are already again adding. Once we go over here, we are adding this both to the stack. Okay, that's the problem. Okay, we have added this to the stack, but again we are adding this to the stack. So adding these element twice into the stack. So we are adding uh, elements twice to the stack. So before adding the element to the stack, we need to check. So checking this element in the stack will be harder to do. So instead of I think we should use this minimum island. Okay. With this problem, we should use queue. Let's try with queue. Okay. All we need to do is change this tag queue. Queue. This tag is let's have the queue. 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 Dot front. Queue. 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 We are doing it queue. We are getting even more. Let's see. So we have already added that element to the queue. But we're again adding the element to the queue. So that's the issue. So what we're going to do is simply have let's create. Okay. Let's create a visited. Okay. What is let's set. Okay. If we have added something to the stack already, we have to add again that to the stack. One input, what you do is change this to row and row. Okay. So this instead of doing it over here, once we find a land, we'll add that land to the stack, but change that position to the water. Okay, just change the position to the water. So don't add that again to the stack. Okay, same thing over here. Okay, find that we have done this. Okay, we are adding twice to the stack. Okay, twice the element adding twice to the stack. So if we go to the previous problem, that will be counting the number of island. What we were go to counting the number of island. In this problem also we have the same specific problem. We are adding the same element like whenever we on the top we go here, we do this. If we go here, let's say, then we go over here for this. We're adding again this. We're adding this again to the stack. Okay, as L. But for this specific problem, it does not matter. Okay, for this specific number of island count problem, this does not matter. But of that, okay. So that we do not iterate twice the same variables. Right. voice. This whole thing is stitch there. Let's change small few things. Okay. Let's do 0, 0. We found the land, change it to the water, and add that land position to the stack. Okay. So if we even change that to the water, we have added its position. So its position to the stack. So we can be sure that we'll go through that position and check its neighbor to see if that is land or not. Okay. So that's let's submit this. Okay. Error. Let's this is okay. Let's solve this problem. So if you go to the graph problem, if you see the max area of an island, so all we need to do is just reject mean island. It's just opposite to that max area of an island. All you need to do is similar same thing. It's just copy these. Uh, let's open this problem. Instead of the mean, we need max. So we need max. So we set it to the 0. We'll again do the similar thing for the count. Count will be same. All you need to do is if our count is greater than our result, we set our result and then we return the result. And then again we have 0 1 instead of land and water, so we do is 0 0 0. Maximum we are getting minimal. This example also we are getting a we have to count. So we are able to count. That's not a problem. We are able to count the result. This is result. That will be first. Let's say result will be 0. Okay. Second problem, we are getting 1. We getting 1? If it is equal to 0, so in second problem we never run this, because we keep on continuing. If it is equal to 0, The answer is not 11 because the island must be connected four directionally. Answer is 6. So that will be 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, that's fine. So we are counting. We are adding element twice to the stack. So if our count is greater than our result, so that is the case. We do this. This could never work. What's the issue here? Colon. So this is working for the minimum island. So the minimum smallest island, we are able to run this code. If we go here, max area of an island, everything should be similar. Let's say I'll get our count. You did make us count from here. Okay? We will create a, if it's equal to 0, we'll create a, you can go plus return 0. The second test case, it should run. We should get 0. But why are we getting 1? Second test case, where are we getting 1? So the stack, we get to the row and column. That is this 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0. So that is 0. So at the end, this much never run. Okay. Good. Simply get result at 0. So okay, we have set the result as 0 by default. What's the issue? Like, it's equal to 0, continue, we skip. Let's say the solution is wrong. Let's say for a second. But still we should get at least for this test case we should get the result as 0. Where aren't was the issue like for the column with 0 we just keep on skipping. See over here. Copy this, let's put into the chat GPT. Please see. Okay, so this will be 0 if 0 is smaller than, it will be 1. So this will be one row and whatever the column. 1 to 1 0 1 1 1 2 1 3 1 4 and till so keep on skipping. In next discussion we don't have question is not even click for an ASCII character 0. Is 0 or O? Last problem we are putting a similar thing. If our grade is equal to sorry, okay. Instead of string, we are getting we have char, but in this specific problem we have int. So instead of 0 0
7 बजे नहीं
0 कति मान्छेले हेरिरहेछ 0 खालि मिडल फिङ्गरहरू नहेर त्यसले ब्लक गरिदिन्छ उसले ब्यान गरिदिन्छ Okay, so we have completed the graph problems, all the graph problems in this specific video. Okay, so from tomorrow we'll continue on going through the graph problem.